Hello. Now we're going to talk about the second half of Chapter 7, Section 3, which deals with the sampling distribution of the difference in sample means. So there it is. So this is a bit of a complicated concept, but maybe it won't be too bad. I'll do my best to try to explain it to you. So first of all, what I want to do is I want to talk about, remind you of what we talked about earlier in regards to Section 7.3, and talk about the sampling distribution when you're talking about, one sample. And so let's say, for instance, our population that we're dealing with is the 12th grade students in a particular school district, let's say, and the variable that we're working with is their ACT scores for those that have taken the ACT. And so let's say that we're given that the mean, the mu of these ACT scores is equal to 21.8. So that for the whole population, let's just pretend there's like 6,000 12th grade students in this school district that took the ACT. So that's our whole population, the group we want to know something about. And we'll say that the average, the standard deviation is 2.1. And so what our population distribution would look like, it would be all 6,000 of those numbers. And there's all these, everybody's got a different ACT score pretty much. And so they would average 21.8, and then the average amount they vary from the middle would be 2.1. And we don't know exactly. Maybe they vary normally, maybe they don't, approximately. Anyway, and so the concept of a sampling distribution is this. We decide to take a sample. Realistically, in the world of statistical inference, we're not going to know this number. We're going to estimate it with a sample. And in this chapter, we're going to pretend like we know it to create the theory that we're going to use later in the year. So we take a sample. Let's just pretend our sample is size 30, like we talked about earlier. That's a bit of a magic number to us, supposedly, because it means our sampling distribution will be approximately normal. And we'll get an X bar. Maybe the X bar we got, the average of those 30 was like, 21.9. It's probably going to be somewhere around 21.8. But if we look at our sampling distribution, so this is our population distribution, would be all these X values, is we're going to graph, so here's 21.8, which is the middle, and so we're going to graph this 21.9. There's our X bar. But then if we were to take another sample of size 30 and get another X bar, it's going to be probably not that. It's going to be maybe down here. Maybe it's going to be 20.7. If we took another sample and found another X bar. So all these possible values of X bar in repeated sampling are what we call a sampling distribution. It is every value that this could take. And they are going to vary, and they will be approximately normal in this case because our sample size is 30. And the central limit theorem tells us that the sampling distribution, every value a sample mean can take, all those X bars will be approximately normal as long as either the population varies normally, which we don't know that here, or our sample size is bigger than 30 or so. So we've got that. And so, of course, we talked about that in section 7.3. But now what's going to happen is we're going to have a second distribution. So this is for, like, let's say District 1. So this is in the one school district in one county. And then in another county, we're going to compare it. We want to see if this county, how it compares to the other county. So we have District 2. And so they're going to have this thing. Like we talked about in the world of AP Stats, we're very interested in comparing two different things and to see which one's better than the other. Anyway, and so what happens here, maybe there's like 7,000 12th grade students in this district, and the mean of their ACT scores is, let's say it's 25.1, and let's say it has a standard deviation of, let's say that's 3.2. And so now they've got their population distribution that's all these, maybe theirs is really right skewed. We don't know. So it looks something like this, a big tail going to the right like that. I don't know. But the mean, the average is going to be 25.1. So its sampling distribution for those guys, you've got all these X bars. They take a sample of size, let's say it's size 40, okay, and they get an X bar. So they get all these X bars just like over here. Theirs is going to be centered around, and this isn't the best drawn normal curve I've ever done. So all these X bars here, that's their sampling distribution. It's centered around 25.1. Okay, and oh, by the way, and I forgot to mention this over here, the standard deviation of those X bars, and this is on your little formula sheet, it is going to be sigma over the square root of n. So 3.2 over the square root of 40, and as it turns out, that is about 0.50596. That is the average amount the x bars will vary from the middle intuitively. And so the standard deviation over here of these x bars, so I'll call this x bar sub 1 and this x bar sub 1 and this x bar sub 2. That's in the first county, that's in the second. And so that is going to be equal to 2.1 over the square root of 30, and as it turns out, that is in fact equal to about 0.38345. And so we've got these two different counties, we've got these two different sampling distributions here. And so what we're going to talk about is we are going to subtract these two things. Talk about what is the sampling distribution of the difference. If we took x bar sub 1 and subtracted x bar sub 2. In other words, if we randomly selected one of these x bars, okay, and then we randomly selected one of these and then subtracted them, okay, what would that distribution look like if we did that again and again? I mean, we're expected, if you say that minus that, so that would be like negative 3.3. We're expecting this one to be 3.3 bigger than the first one, but there's going to be variability going on. So, all right, so how is this thing going to vary, this sampling distribution of this difference? All right, well, the mean of this difference, x bar sub 1 minus x bar sub 2, you just subtract the means. It's going to be 21.8 minus 25.1, and that is equal to negative 3.3. And that is on your formula sheet, by the way. So here's our relevant formulas for us. They are for a sampling distribution in regards to a mean. All right, so sampling distributions for means. You notice when you've got two samples, the mean of when you subtract them, you just subtract the means, and there's the formulas for standard deviation. And it goes back to what we did at the end of chapter 6 in regards to whenever you subtract two random variables, you have to add their variances, and so that's what's going to happen here. So the standard deviation of x bar sub 1 minus x bar sub 2, that's a bit kind of cumbersome notation, but that's what it is. It's on your formula sheet. Is you would say, well, we have to add the variances, and so we would have to square that. All right, so the variance of our x bar sub 1, it would be 2.1 squared over, and then the square root of 30 squared is just 30. So it's 2.1 squared over 30, like that. And then the variance over here, the variance of x bar sub 2, you'd square that. That'd be 3.2 squared over 40. And so what standard deviation would be the square root of this variance, 2.1 squared over 30, plus that variance, that'd be plus 3.2 squared over 40, and that, in fact, is equal to approximately 0.63482. And so there is our standard deviation. And so what the sampling distribution is of this when you subtract it, what's happening there, if you were to take one of these x bars and randomly select one of these x bars and one of these x bars and subtract them, you would get a difference. And so I'll put that difference there. But if you were to do it again, you would take that minus that, you would get a different difference. Okay, and if you kept doing it, if you kept randomly selecting an x bar from there and an x bar from there and subtracting them and getting differences, they would vary. Okay, and what this is saying is the average of the difference, okay, the mean, this guy, these differences will be centered at negative 3.3. Okay, negative 3.3. And then their standard deviation would be that. We found that. And they will be approximately normal. All these differences will be approximately normal if one of two things is true. Either the distributions varied approximately normally, so that would have to say that in the problem. It would have to say the populations are varying approximately normally, which that's not the case here, or both your sample sizes are at least 30. So in this case, you would say both the sample sizes are at least 30, so my sampling distribution is approximately normal. The other big condition in this chapter is that our sample sizes can't be more than 10% of our population, or in other words, our population size has to be at least 10 times our sample size. And that's no problem here, because our population Here, the population size has to be at least 300, which is 6,000. Here, the population size has to be at least 400, and it's 7,000. That is the theory behind what we're doing. So let's do now. Having said that, now let's see if we can do the problem. So here's your formulas in regards to the sampling distribution of the difference in sample means. So there you can just subtract the means, but then there's the formula for the standard deviation. And you'll have approximate normality if one of those two things is true, like I said. And so, all right, so let's see if we can look at this. So it says, some of the fifth grade students in a large school district were put through a computer training program to improve their reading skills. After the program was done, all the fifth graders in this district were given a test to measure their reading aptitude. The scores of the students that went through the program had a mean of 82.4 and a standard deviation of 4.1. So those are the ones that went through the program. The scores of the students that did not go through the program had a mean of 78.1 and a standard deviation of 6.3. So the ones that went through the program did do a little bit better on their reading aptitude test. Let x bar sub p be the mean of a random sample of 40 students who went through the program, and x bar sub n be the mean of a random sample of 50 students who did not go through the program. So what's going to happen in essence later in the year, we're not going to be given these population values, and we're going to use sampling to figure it out. And so we're doing this right now to create the theory to work with that. So what we're doing is we're taking a random sample of the students that did this and a random sample of the students that did not go through the program, and we're going to work with the difference between the two if you subtract it. Now, if you think about it, if you get a random sample from this and a random sample from this, and you subtracted them, well, you're expecting the difference to be like 4.5 because that's the difference in the mean. But there's going to be variability. Well, how can we describe that variability with the standard deviation? So first of all, right, you're asked to describe a distribution, so you have to cuss. So in regards to the center, all right, in regards to the mean, so the mean of this thing of x bar or of x bar sub p minus x bar sub n, you just subtract the two means. It is going to be 82.6 minus 78.1, and that is 4.5. All right, but now the standard deviation, that's like what we just did with that example I just did. The standard deviation of our x bar sub p minus x bar sub n is that formula right there. And so that's what we'll do. And so that one is going to be, the square root of 4.1 squared over 40 plus 6.3 squared over 50, and that in fact is equal to 1.10184. So there's the description of our center. This is a description of spread, the standard deviation. Okay, it will be approximately normal. Okay, all right. The sampling distribution, the sampling distribution of the difference of x bar sub p minus x bar sub n will be approximately normal because both sample sizes, and stay what they are, 40 and 50, are greater than 30. And so there we go. And so you're asked to describe the distribution. So you'd write a paragraph, which I didn't leave myself room here, but you would just say, well, the sampling distribution is approximately normal because of the large sample sizes. The center is described by the mean of 4.5. The spread is described by the standard deviation of 1.10184. And then the unusual values is taken care of in regards to the approximate normality. Approximate normality will also describe the nature of the of the outliers. And so there's our sampling distribution, our mean and standard deviation. And so then the kind of problem we'll be asked is this: what is the probability that a random sample of 40 students who went through the program will have a mean score that is at least 5 more than the mean? So what's the probability that this guy is going to be 5 more than that guy? And so we have our sampling distribution here, so we can answer that question. And so that will be normal CDF. So I'll say normal CDF because we have a normal curve. It says at least 5. That means from 5 to infinity. So that is my lower bound. That is my upper bound. Okay, the mean of all of these differences, and I'll put, mean sub diff for differences. You can just put mu or write the word mean. And so that is going to be 4.5. And then the standard deviation of my differences is going to be 1.10184. And so when I find that value, I get 0.32499. And so in other words, it's not that unusual a thing. It happens 32% of the time just by sampling variability. So it wouldn't surprise us at all if we picked one of the students who went through, or if we took samples like this, that the sample of the students that went through the program, that its mean is 5 more than the other one. Okay, so that is that. Thank you for paying attention. I wish you much success in the sampling distribution of the difference in sample means.